Welcome everybody to the last meeting of E340 599. Thank you for everybody for sticking it out. I know it wasn't always an easy ride. I appreciate you all being willing to do these in-class presentations as usual. These are live streamed and recorded and made available. I hope that that's something that you like. If you don't want your presentations live streamed and recorded, tell me and I'll turn off the recording during your presentations. So today we have the last 4 presentations scheduled. Jeffrey, Antonio, Devin, and Brian. Looking forward to them. Thought everybody did a great job last week. I hope everybody can learn from each other. I realize next year, in the spring, when I teach the spatial modeling, and then if I do this again, I'm going to ask people to do these a little earlier so that there's more time for feedback and improvement of their projects. Because people did a great job, and it's worth would be worth spending a little time iteratively refining these things. As I mentioned, I do need you to write up a critique of your classmates' projects. Doesn't have to be very elaborate, but it is important to show that everybody listened to each other. And I need those by tomorrow so that I can send them around so people can make final updates to their projects based on the feedback. So that is a graded assignment, a small grade, but nevertheless, a little bit of extra credit. I need the presentations and the notebooks by Friday night because technically grades are due at the very latest by Monday of next week. And so I need to be able to go over them and review them. If you need an incomplete to finish things, let me know if that's essential. As I mentioned, it's not absolutely required that, in fact, I said didn't ask you to do a video, but if you'd like to do a little video of yourself demonstrating the app once it's ready, that wouldn't be as detailed as what you're doing here in your class presentations, but something that would a 5-10 minute video to show people how to use your app. That would be most welcome. I'm happy to give you extra credit for that if you do that, but it's really not required. And you're not really done with the class until your application is uploaded as a NanoHub application. And given the timing that we have, that may or may not be possible. Because it takes some time for NanoHub to actually go from your requesting them to upload it to actually doing it. And so my requirement is that you have your file in GitHub and have put a NanoHub pull request to ask them to put it online. Ideally, it would be online before Sunday night so that I can have that as part of your grade, Monday morning so I can have it as part of your grade. But if NanoHub is slow, I'm not going to take off, but you're not really officially done with the classwork until your app is up on NanoHub. And if you need help getting it uploaded to NanoHub, talk to Josh or Giuliano, who are the experts on actually getting that implemented. Are there any questions about that, besides the fact that I have GitHub typed GitHub on this slide? Any questions about that? Okay, so we have the order of presentation was Jeffrey first. Jeffrey, are you here and are you ready to present?
Yeah, I can go.
Okay, is it okay to record it?
Yeah, that's fine.
Okay. I will turn the screen over to you and
okay. Okay, so I'm talking about modeling synchronization in neurons. Um, so I'll start with a little background of just the basics of neurons, in case anyone doesn't know or is not familiar. So they have, in the resting state, they have a potential of around negative 0.7 millivolts, and this is due to concentrations of different ions on the inside and outside. Potassium is on the inside and sodium is on the outside. There are more, but those two are the main two types that influence the action potential. So there's you have these dendrites that take in signals from other neurons, and if the signal reaches a threshold of about negative 0.5 millivolts, then it sends the action potential down through the axon, and these synapses are connected to other dendrites, and the process just repeats. So here is just the action potential. What happens after the threshold is reached is voltage gated ion channels open up, and there's an electrical field and chemical gradient that are acting on the ions that cause them to move around. So that is the basic idea. And most broadly, there are two different types of neurons that exist, I guess, excitatory and inhibitory. And I'll actually talk about those more in a second. So I said there are ion channels that are kind of, when they open, they're kind of responsible for passing the action potential along the axon. So when you're thinking about modeling this, parameters you might want to consider are how many of the ion channels are open at a given voltage, because the sodium and potassium channels don't open at the same voltage. So you can introduce this parameter, which is a measure of how many ion channels are open for a given ion. And if you look at this picture, you can see there are positive charges here on this extracellular side, and negative charges are accumulating inside. So this looks kind of like a capacitor, and you can think of the membrane as a capacitor. But because of the channels and also the fact that it's not ideal, an ideal capacitor, there are ions, and so current passing through it. And something that might be worth considering is how easily they pass through. So you can introduce a conductance parameter when thinking about the process of modeling. So what this model that I'm going to be talking about considers is collections of neurons. More recently, I guess that's kind of where the interesting questions are, is how neurons interact with each other, and what kind of behavior can arise from them, specifically cooperative behavior or collective behavior, I guess. So some questions related to this are how can you model these interactions, and how do these interactions, how are they represented in the dynamics of the model? So I've read that a lot of cognitive functions like memory and learning processes result from synchronized neurons. So I think it would be interesting to see if you were able to monitor the neurons that fire for it. Memory, is there some kind of limit cycle or something that you can like mathematically describe the kind of physical idea? But I haven't really thought about it too much. I think it's an interesting question. So I put it here. And also synchronization of neurons when it's a large number can result in seizures, and that's what the two papers that I've been looking at consider. So when it comes to modeling large-scale systems, it doesn't make much sense to use units of single neurons. So what they use are these objects called cortical columns, which are collections of neurons, which are basically the definition is they're densely, you can see from this picture that here's a column and there are a lot of arrows inside, meaning that the neurons in the column have strong connections between them, and between columns they're weaker. So what these columns represent are neurons that are connected to each other and go off to a specific area somewhere else in the body. So you can kind of consider them as distinct units, but it's also not really an official kind of component of the brain. It's just something that makes modeling the system easier. Yeah, it's good for large scales. So now I'm going to give a little intuition behind how the model comes about. So when you're thinking about how to model neurons, the main I guess function is to fire an action potential. So you're going to want to look at the voltage or potential. And so I mentioned earlier that that can depend on the conductance and fraction of open ion channels through the membrane. So you would probably expect this V to depend on those two parameters, as well as V itself, because when the threshold is met over here and the action potential starts, the channels start opening, and as the ions leave the inside to the extracellular space, the potential or electric field starts decreasing and ends up reversing direction. And so does the chemical gradient, because the ions are diffusing. So what happens is at a certain point, the voltage ion channels also become closed again. So the potential begins to return to its resting state. So you can assume that V will be a function of these variables, and it's also a function of the Z, which is the inhibitory potential, because you can kind of think of Z as something. So here you have this inhibitory potential. And the way I think of the inhibitory potential is sort of like if you've written code that uses a buffer, it's something that kind of, I guess, fractions or rations out information as it's being processed so that it's more manageable. And so if you think of C as a buffer or V as the information, then you can consider Z is probably going to be a function of V. Yeah, when I was learning about buffers, I found this answer on Stack Exchange kind of describing it. In case you don't know what a buffer is, it describes it in terms of candy. So you can, yeah, express Z as a function of V. What else? You have W, I forgot to mention that. It's the fraction of open potassium channels, which is also, you can think of M as, okay, so M is the fraction of open potassium channels. W is the average number of open potassium channels in the cortical column, because you're considering multiple neurons in potassium is kind of more, you could probably have one for a variable for sodium too, but then it becomes a 4-dimensional system. So I guess potassium is a little more relevant to the initial firing of the action potential, and it's also and because potassium channels end up closing. So what you can expect is probably this is a function of M for potassium and also D. So you get this. And then here are the models of the equation, which, I mean, the explanation I just gave was with some hindsight. So obviously I was going to include all the variables needed, but you can see this, I mean, hopefully the explanation made sense, but you have the conductances in ion channels. You have here this. And this first equation is actually just if you equate the equation for capacitance with Ohm's law, you can derive this equation generally, and then just plug in these values that arise in the neuron, such as the neuron voltage. This QV, I forgot to mention, is a firing rate. Since you're considering columns with multiple neurons, it's important to consider the average firing rate of the neurons in those columns. You're not just considering one neuron. And these A parameters are relate the connections between excitatory and excitatory neurons. IE is inhibitory to excitatory, and NE is an external connection. So you have your I is an external current if you want to input current, but it can also, this I can also be 0. Z also depends on I. And your W if you look experimentally at how the potassium channels open and close, you see it's exponential. So you're going to want an equation like this to model W. And phi and B are just scaling parameters to give reasonable results. So this is the uncoupled equation or equations. I guess here is the equations for the firing rates. 1/2 times this parentheses quantity gives a number between 0 and 1, and multiplying by the max value will give you a firing rate between 0 and the max is a function of the potential. Here, this is between 0 and 1, where 0 means all of the channels are closed and 1 is all open. This is the coupled equation. You can see when it's the same thing basically, except you have this term here and here with C. It's a coupling term. And when C equals 0, you get the first equation I showed you. And that corresponds to uncoupled. And when C equals 1, this first term here disappears and you get, so everything depends on this average firing rate here, where the average is over all of the cortical columns. So if you look at this, you'll see that means that all of the dynamics for each column are the same because the independent firing rates disappear. And same for C and W. So here are some results from what I've been doing. You can find limit cycles in the system. This doesn't look exactly like the one in the paper, but also the parameters that they give in the paper didn't end up working for the model, so I had to adjust them some, and this is the closest I could get. But it's a limit cycle, so I guess it's okay. You can look at how it synchronizes when you plug in the coupled equations and adjust the C parameter. And then this is something that wasn't done in the paper, but something I was interested in looking into is since they were modeling seizures, I wondered if there was a way to kind of desynchronize the system, since seizures are a result of highly synchronized, large-scale synchronized firing. And so I found a certain medication, I forget what it's called, but it basically functions by blocking the sodium channels in the neuron. And when I plugged in like a scaling value into the equation for the conductance through sodium and adjusted it, you can see that it kind of, the synchronization dips down a little bit and then picks up again, I guess, with some, as time passes, the results become not so important maybe. But initially it kind of dips down, so I thought that was interesting, and I was glad that it showed something that I was kind of hoping for, because a lot of the other things I've tried to do didn't work. So that is my results, and here are the sources. You can ask questions. I can also go to the actual code if you want to see other things that I have in it. I don't care. But yeah, that is all.
Okay, great. Thank you. That's rather different topic from the ones we've covered in class, but structurally the equations should look familiar to people. Uh, let's see if people could ask a couple of questions, because this is an area it's an important area which we didn't really have a chance to talk about much in class.
I just have one question. The 3D plot, was that something that you generated?
Yeah, that's I think I used a contour plot or parametric plot. I don't remember.
But did you still wrap it with tellurium, or did you write the equations differently?
No, I got it from Tellurium.
Okay, cool.
And if you can demo it, the app, that would be great. So the main thing you're trying to show here is that as you change what happens when you change the coupling? Is that the main idea that you're trying to get across?
Yeah, so I will just show this. Yeah, I start with some background. And then I just started out with the single equation. Yeah, this, or the uncoupled equation, I mean. And this is a long thing where it shows this. Oh yeah, this is the code that makes the 3D plot. Yeah, I put the variables in Tellurium there. But this shows the eventual kind of how it changes. This is this lets them kind of adjust the value themselves.
So DV is the bias. So you're hyperpolarizing or depolarizing the neuron to see if you turn on and off the action potentials.
DV is yeah. It's variance. So the paper talks a little bit about chaotic dynamics, and I've been trying to implement that, but I can't figure out how to compute Lyapunov exponents, so I think I'm just going to delete this part. Probably the whole section on chaos.
Well, you should still be able to see chaotic results. So let me understand. Just we could talk more offline too. There's a lot you've got a lot to present. You've presented a lot, and so the basic idea is you first show a single oscillator. Is that right?
Yeah.
And that single oscillator, you had a bias voltage, right? That you could add to it. Is that what the DV was?
DV is a threshold, or yeah, it's a variance in threshold in the potential. So it comes up here in the firing rates. It's like variance between like the threshold required to fire an action potential.
It's a gain, basically.
Yeah.
And why are you picking the that to adjust? Is that controls the way the single neuron fires?
It controls the firing rate, or it controls the firing rate of the column. So yeah, you can see how dynamics change for different firing rates.
So I should, as I change dV, I should see the frequency of oscillation change.
Yeah.
And if I changed I delta, I should be able to switch from firing to non-firing.
Yeah.
Because I delta is the bias, so I could be able to depolarize or hyperpolarize my membrane.
Yeah, I think that's how it should work.
Okay.
Right.
Okay, so if I run two of these independently and they're not coupled, I should see basically the same thing twice, but if I had slightly different dVs, the frequencies would be different. Is that right? Was that not clear, or did I lose?
I just cut out for a second. I didn't hear you.
Right. So suppose I have two. So I have one neuron, and now I can turn it on and off by changing that I delta function, that I delta value, and I can adjust the frequency of the oscillation, I think, by changing your dV, if I understood you right.
Yeah.
So you could demonstrate that by allowing the person to change those two parameters and show that as you change I delta, you go from no firing to periodic firing. And as you change dV, I can change the frequency, assuming that that's what that does.
Okay.
And now, if I have two neurons with no coupling, and I plotted those, I would see basically the same oscillations. If they had the same value of ID and delta V for each one, I should see them oscillating at the same frequency. They should both oscillate, although the phase might be different.
Yeah.
Okay. And now if I couple those and they're already synchronized, I would expect the coupling wouldn't do much.
Yeah.
But if their frequencies are adjusted, so the dV is slightly different between the two, then I would expect. So this is when they're both in phase and uncoupled. Is that right?
Yeah.
And so now I'm going to couple them, and what I would expect is there's some kind of beat pattern where I get a modulation of the two neurons together. So I get a beat. Is that so? If I turn C on now, what happens?
They grow.
So they're staying synchronous. Okay. And now if I change dV so that they're not in the same frequency, what happens?
I can. It's.
You didn't assign it to a. Okay, so you're going to change one and not the other. So now you have a convergence. What was the normal value of dV?
Something less than 1.8.
Okay, but so you better, so, oh, so, but wait a sec, so those are set to be different by default? If they're different by default, if they're different by default, why is the frequency of oscillation of the two neurons the same when it's uncoupled?
I don't know.
Okay, so something isn't quite doing what you expect, I think, in that case. Because classically what you do, I mean, so normally, I mean, there's no right or wrong way to do it, but when I've seen this done before, what you would do is you'd build one neuron oscillator, you build another one, then you look at parameters that control the amplitude and frequency of the oscillation, which you've looked at. And so if I change dV, you said that what dV does is it changes the frequency of oscillation. And so now I do that for one neuron, and I see how it depends on the frequency and amplitude, and presence or absence of oscillations depend on the parameters I can pull. And now I couple a pair. If my two neurons are oscillating in frequency, with the same frequency in the same phase, when I couple them, it doesn't do very much. Maybe the amplitude goes up a little bit, but not much. Now I switch it so that the two neurons are not in the same frequency by default. Now when I couple them, depending on the strength of the coupling and the phase difference and the frequency difference, I could either have them in train, in which case they would uncouple to oscillate separately. If I couple them linearly, I'll get beats, where the frequency of the beat is the difference in frequency between the two oscillators. And the mean frequency is what the high frequency. Or if the coupling is nonlinear, I could get them to entrain, in which case they oscillate as if they were the same neuron, even though the natural frequencies are different. Or if the coupling is very strong, I get a chaotic oscillation, where I get something that looks like a beat pattern, but in fact, I get a chaotic relationship between the two neurons. And so I don't know what, I mean, that sort of, those are the things that the pair of neurons can do to each other. And I don't know quite how far you've gotten with your demo in terms of displaying that. You showed and when you showed the basic limit cycle, tell us again what the limit cycle was. The limit cycle was the base oscillation, but then you seem to have a drift in one direction.
Yeah.
What was going on with that? So what's the, tell me, so as time goes on, the value of Z keeps increasing. Why is that?
So it doesn't always increase. I don't know if I can. So around in this area, it goes from
Okay,
it goes from increasing to decreasing. And at a certain point, you hit a limit cycle.
But Z can't keep going forever. So what happens when Z comes out of its range of? So I guess, I mean, you come onto, this looks like a Shilnikov attractor. So you'd expect in 3 dimensions that you'd see an oscillation that drifts, and then you get to some critical threshold where it jumps out of that and starts over. Does it do that?
I haven't seen that, and even when increasing time.
Well, why don't you run it for longer and see what happens? So. which is the start and which is the end, by the way?
Here's
Starts there. Start. Okay, so value of Z keeps going up and up and up and up and up. There, it looks like you're collapsing onto a limit cycle. But in the other one, the value of Z keeps increasing. Does it ever get to a point where the value of Z stops increasing?
It probably takes a long time when you run it for a while. Z kind of goes up and then kind of logarithmically flattens out. But
So
it's
it'd probably be a good idea to actually plot at Z versus time, W versus time, and V versus time. And if the frequency of oscillation is too high, plot the envelope of it. So plot the maximum or minimum or mean value versus time. So you can see if you're reaching a stable limit cycle or not. I think that would be, it's very nice to see the 3D one, but sometimes seeing the 1D plots is helpful as well. And this is for a single neuron or a single cluster column. Is that right?
Yeah. Yeah.
Okay. Okay, and so then you couple. Okay, so you could extend that to do that. And then what am I seeing there with the beat pattern that you just went past? There, what's that?
This is just another pattern that they made in the paper that I was trying to get to work. And I was also going to talk about chaos and stuff with it, because you can see it's not really, it kind of looks periodic, but it isn't.
Well, so that if I have two oscillators that are linearly coupled and the frequencies are incommensurate, then I'll see something that looks like that. That's not necessarily chaotic.
This is just a single neuron right here.
So this is a single neuron. So I'm in a regime now. Okay, so I'm in a single neuron regime. So you're going around your spiral, and then you've got that. This is a class. Okay, so this is Shilnikov, where you come up, your V value goes over. What's the vertical direction here? What am I plotting? What are you plotting? V?
Vertical is V, and the horizontal is time.
Okay, so it would be useful to have in register with that Z and W.
Okay.
Because what should be happening is that Z is increasing and then it jumps and increases and then jumps. And that's why you're seeing what you're seeing there, I think.
Okay.
And again, I mean, so it could be chaotic. It's hard to tell from just looking at one of the variables. If you really want to do the Lyapunov exponent for this, you have to take what's called a Poincare section, where you don't plot the continuous variable, you plot the value now and the value at a certain time later and a certain time later and a certain time later. So you turn it into a return map.
Okay.
Josh, remember when Bedang did his little paper? There's that paper of Ott at Maryland who did the Lorentz attractor to show how to go from the time continuous to the return map.
Yeah, I do. I do remember.
Okay, if you can send him a link to that is a very simple, mathematically very simple way of doing the analysis. That would help you with that. Okay. And then you were going to do a coupling between two neurons. I think you showed us some of that.
Yeah, I had.
And I didn't want to break your model, but I just wanted to try to understand.
I'll figure out that.
Okay,
later.
so so the difference here is because so it looks like you had a different value for dV in these two neurons, right?
Yeah.
Okay, and that they're oscillating with the same frequency but different amplitude. So it looks like dV controls amplitude rather than frequency. And so now you turn on the coupling, and what happens? They lock, but the thing here is that it's less interesting because the frequencies are the same. So what you want is a parameter where the two neurons have fundamentally different frequencies when they're uncoupled. Rather, okay. Yeah. So there, what's that? What happened? What's this one? What's this model?
This is the kind of the one that was up above with the pulse from up above, and this is just random initial conditions.
So what's the difference between V1 and V2 here?
This.
I mean, what's
dV1.
Okay? So dV under. Okay.
So here's V1, and this is 0.4.
Okay, so you started with different initial conditions and different values of that parameter. And is the oscillator frequency the same by when there's no coupling? Let's look at the uncoupled case. The oscillations are different frequency, and now you put in coupling. Okay, now you couple them. Just leave it a second. Okay, and so they come into phase lock, which is good. And then you could make the coupling stronger, and you get a chaotic locked attractor. So okay, so this is nice. So you could play with not just this coupling strength, but the difference in native frequency between the two of them, and see how the coupling occurs. Do you ever see locking that's not 1-to-1? Do you ever see 1-to-2 locking or 1-to-3 locking, where one oscillates twice as fast as the other?
No, not. I've only used 2 neurons, so what happens is, well, it's hard to look at this. You get just this average firing thing begins to dominate rather than the independent firing one. So whichever has the higher firing rate is going to be
Dominate.
Dominant. Yeah.
Okay. Okay, well, I think that's interesting. So I think if you can present that clearly, it's a good exercise. What would somebody who ran this exercise learn? What would the takeaway message be?
I guess and gain some insight into well, at the end I have hopefully this works. This is for the anticonvulsant medication that blocks sodium channels, and so this scale 1 and scale 2 change how much sodium is crossing the membrane. And as you kind of change it, you see that they kind of synchronize, but not really all the way.
So if I turn off the scale 1 and scale 2, they lock. And now if I turn scale 1 and scale 2 on, they unlock, they don't lock.
Well, they should initially be this. Okay, so something else is going on here.
I mean, that's actually looks like a pretty interesting thing because your pulses, your bursts are getting shorter. So it might be interesting to run it for longer and see what the burst dynamics is. So I think you've got a lot of really interesting material here. Maybe quite a bit of interesting material. But I think you should try to think a little bit about how to present it so that people can. I think there's a lot to learn from somebody doing this, but the question is, how do you present it so that somebody playing with this can understand what they're seeing? What's the insight that they get out of it? I think it's great that you're thinking about an anticonvulsant. That's very interesting. Are you applying some kind of noise to the system, some kind of external noise or kick to the system?
No.
Because usually the issue is with these things is once the neurons have synchronized, they're going to stay synchronized. So if you apply the drug late, in other words, if they synchronize and then you give the drug, it's not going to desynchronize them unless there's some kind of noise that pushes them apart, pushes the oscillators apart.
Yeah.
Okay, well, we're going to run out of time. This is fascinating, but we're going to run out of time if we don't continue to the next talk. I'm happy to talk with you more about it. I think it's a really interesting piece of work. The audience hasn't said much, so I hope you're making notes. Please, again, part of your assignment is to make a critique of each of your classmates' work and send it to me so I can pass it on. I need that for everybody for tomorrow, so that everybody has that when they're preparing their revisions. Okay, Josh, do you have anything else to say on this? If not, thank you very much. That's great. And Jeff, appreciate that. And we'll go on. I think Antonio, you're next. Nico, you're next on our list.
Yep.
Is it okay to record you?
Yeah, that's fine.
Great. Okay. Take it away.
Alrighty. So first off, I just want to preface my presentation with saying that while I have a majority of the computations done, it's not cleaned up and refined to the level I want it. So I'll be spending some more time after this, really kind of making it clear what I want to demonstrate. But basically, this is a model of tuberculosis. And so throughout this model, I'm going to be kind of adding a vaccine component as well as an antibiotic resistance component. Sorry. So TB is a bacterial infection of the lungs, and it works on time scales of years rather than months or days. So a lot of these simulations are going to be much, much longer, on the order of 20,000 days. It is also currently the most infectious disease in the world, and it has a tendency to become resistant to antibiotics, which is extremely dangerous, especially in lower income countries, specifically prisons. There's a problem in Russian prisons or countries that were formerly the Soviet Union of inmates developing TB. They only have 1 or 2 antibiotics to treat them with. Resistance develops, and this super resistant strain is spread throughout the prison and ultimately the country. So this is one of the arrow diagrams I've been working on. So I'll give you a quick overview of the model, and then we'll kind of break it down. So this S is your susceptible population, which then becomes latently infected, which then develops into the early disease. The early disease then can either become smear positive, smear negative, or non-pulmonary. So smear positive and smear negative refer to a sputum test that they run. So they have people They collect samples from the lungs either by having patients cough or extracting directly. And then they run a plate to see if they can find the active bacterium. If they can't, it's smear negative. If they can, it's smear positive. And what that basically translates to is that smear negative patients are slightly less infectious than smear positive. And non-pulmonary patients are patients whose TB infection isn't actually in their lungs, but any other organs of the body. So they actually don't show any infectivity. All three of these groups can be identified for treatment here, or they can spontaneously recover. There's also some pathways where you can get reinfected during your treatment and move back to the early stage, or after you've recovered, you can be reinfected given at a lower rate. So you're like 35% resistant. I'm sorry, you're 65% resistant to reinfection based on the literature, but you can be reinfected and move back to the latent state. And obviously, over the course of the early treatment and recovered, you can still pass away. So, breaking that down a little bit more, I'm trying to see if there's anything in this paragraph I want to highlight. Okay, I think I got that all. So here's some of the assumptions that we're making. Only, and excuse my spelling too, like I said, it still needs to be polished up a little bit, but only susceptibles are reproducing. The original paper had a lot of stratifications. So they stratified it by age and by fast and slow progression. Here, I'm just going to assume adults and fast progression. I'm assuming that there's no spontaneous recovery from an early infection. And only those in treatment, smear positive and smear negative, are infectious. And people in the early infection cannot be identified to be treated. So moving into the model, I'll just kind of go slowly so you can kind of just glance over the code, but it follows the arrow diagram that I showed earlier. Also, since we have a birth rate, I'm going to be working in fractions. So if I wasn't going to work in fractions, everything would just kind of be this exponential growth over time. So working in fractions allows us to get kind of steady state variables. Okay, so here's just the time series of the original model. So you can see it, 100% of the population obviously starts out as uninfected. And then it takes, on the order of 5,000 days, so several years before you really see a decline in your uninfected population. And this infectious fraction is kind of hidden below the treated fraction as well. So here we're going to scan through some different variables and see how they affect those steady state values. So scanning through N, which is interactions per day, it's essentially instituting a quarantine. As you decrease N, it's very similar to people not interacting with other people as much. So, this is a stacked bar graph. So blue is going to be your susceptible, your red is going to be your infectious, non-infectious, and then your green up top is going to be your recovered populations. So you can see as we increase the number of interactions per day, really quickly, your population is dominated by infectious and non-infectious cases of TB. And so next we're going to move into scanning through resistance to reinfection. And so that's what I was talking about earlier, where after you've recovered from your infection, this will be how resistant you are to being reinfected once more. So again, starting at 0%, and then 65 is the literature supported value. And as we increase that, you'll see that it's just a pretty steady trend towards susceptibles growing and recovereds decreasing. And infected obviously is decreasing. And the last thing I want to investigate with just the simple model is the treatment efficacy. So here as we increase the efficacy of the treatment. Again, we can see that the final fraction of the susceptible population increasing, and then kind of finding this steady fraction there. The recovered's obviously increasing as your treatment is becoming more effective, and the final fraction of cases decreasing. So here, same variables, but we can use sliders to look at the time series of each of these. So again, this is N, your number of interactions per day. And so as we increase those, we see that the reaction, or I'm sorry, that the infection develops much, much quicker. And I think one of the things I want to do with this is add a duration slider too, so that we can shorten this duration down and really kind of focus on the initial few days as we increase this N. And we can see at 20 days, your infectious fraction dominates over your non-infectious fraction. And in a matter of a few days, everybody has been infected. Whereas if we drag it all the way back down to 0, and actually, I'd be interested to know if anybody figured out how to make the slider only calculate the current state it's on. I did this continuous update, which is false, which waits till you release the click of your mouse, but it still seems to go through all of the variables from where you started and where you ended.
Because inside the slider, I think you just have to move your parenthesis.
Oh, okay.
Try it. Other way. Put it inside of the slider.
Oh, saying, okay, I see. That's much better. Okay, thanks, Professor. I appreciate it. Similarly, adjusting Q, which is again the resistance to reinfection. And if we say that people don't get reinfected, and I'm sorry, people always get reinfected and people don't get reinfected. And then similar to Z, which is, I'm sorry, I'm blanking on. A Z is the efficacy of your treatment. So as your treatment is not effective at all, you see that the time span of complete infection is shortened, and your recovered fraction is dropped significantly. And if your treatment is 100% successful, you see that your infected individuals drop significantly and your uninfected population remains high. So now I'm going to start adding in one at a time resistance and a vaccine model. So starting with a vaccine model, basically what we do here is, and I apologize for not having an arrow diagram drawn up for this, but it acts as a gateway almost. So your susceptible population can move into your vaccinated population. And then just for curiosity, I also implemented a vaccine complication rate where people die upon vaccination, which is incredibly, incredibly low. But once in the vaccination state, they can move to latent infection at a decreased rate. They can die by natural death, and they can move back into the susceptible population after the vaccine has lost its efficacy, which default is about 40 years. So looking at the parameters for vaccines, we're going to say that about 0.2% of the population is vaccinated every year. As a default, it prevents infection by about 50%. It lasts 40 years. And as you can see, the risk of developing, it's called BCG-itis, is the disease that ultimately causes death from this vaccine. But you have this chance of developing BCG-itis, and of that, about 50% die. So the amount of people that die from the vaccine are incredibly low. And then we can see that as compared to the original model. So keep in mind that here the uninfected is not including the vaccinated fraction. So here we can see that you vaccinate rather quickly, and then as the amount of susceptibles decreases, your vaccination rates also decrease because you have less susceptibles to vaccinate until they reach this steady state. And ultimately, your infection stays slightly lower than originally, and it also kind of reduces that initial bell curve. So here we're going to scan through the rate of vaccination of the public. Again, this is kind of one of those things I haven't cleaned up yet, but here the colors are obviously on the legend, but the white space indicates how much of the population is vaccinated at the final time. So you can see as you vaccinate the population at a higher and higher rate, more and more of the population are vaccinated. And right about here, 2 or 2.1, you see that about 75% of the population is vaccinated, and you've essentially eradicated the disease from the population. So I'm going to clean this up a little bit and do a little bit more investigating as to how and when that gets eradicated. I might also change some of the other variables such as efficacy rate and stuff like that. Here is the efficacy rate of the vaccine. And so as you can see, as the vaccine becomes more and more effective, your uninfected population is obviously going to grow. Your infected population is going to steadily decrease, as is your recovered, because less people are getting infected in the first place. So here, I'm just letting the user adjust some of the variables themselves to observe the time series. So if we adjust the rate at which the population is vaccinated, we see this vaccination curve quickly increasing. And we see ultimately as this flattens out, it's a result of the fact that you're kind of eradicating infections as you go. So about there, you see that there's actually no decrease from the maximum vaccination fraction, which basically says that you've eradicated the disease. And then again, as you decrease, you can see that you're not eradicating the disease completely, so you're still having people die off until you get to 0. So here we're going to adjust the efficacy of the vaccine. And this is a similar thing I want to do for the other sliders as well. You can change the duration of it. But we can see that as you increase the efficacy, again, you're going to see that the maximum of your vaccinated fraction doesn't change. But the tail end, you don't have people dying from the vaccinated group. So you can stretch this out. I'm increasing the duration here. There it goes. But as you decrease this vaccination effectiveness, as it'll load, but you see that the infection population still gets infected and causes death among the uninfected and vaccinated populations. But the max again doesn't change because you were not affecting the rate of which the population is getting vaccinated. So here we're going to add antibiotic resistance. And this was pretty complicated for me to do. Essentially, I cloned the entire model. So you're smear positive, you're smear negative, you're treated, you're early, you're latent, and made basically a resistant clone of all of them with some changes to the rates. So here we see that susceptibles become resistant when they're infected by other resistant strains. And I think I'm going to change these a little bit because there is an energy cost of the bacteria to being resistant. So that should have an effect of decreasing the infectivity a little bit, so that in an equal playing field with no antibiotics, there's a reason that the non-infection or the non-resistant strain is the wild type. But moving on, we have here that the vaccine prevents you from being infected by the resistant and the wild type strain equally. Here it's just a clone. And then when you get to your treated category is really where you start seeing an increase in your resistant cases. So this is recovery, not to be confused with the resistant cases. But here we see that resistance develops during treatment at a rate of about 17.7% based on the literature. So your psi, there's a lot of parameters I have to remind myself, but so your psi is the duration of your treatment, how people leave your treatment. So the percentage that you're become resistant during your treatment essentially is what that is. And here is your kind of reinfection. So as you go from treatment to reinfected, but you now have a resistant strain. So basically this is going to be people that stop taking their drugs early. And I don't know if I mentioned this, but since the disease is on a pretty long time scale, the treatment is also on a long time scale on the order of 3 to up to 30 months. So people are taking, it's commonly 9 to 12 months. So daily antibiotics with the side effects, which can include diarrhea and nausea, for usually 9 to 12 months. So there's a high percentage of people that stop taking the drugs too early, and then they end up developing resistance. Otherwise, like I said, everything's just kind of cloned. So you have a smear positive and a resistant smear positive with just slightly different rates, because the resistant strain is about 50% more resistant to treatment than the wild type. And then same here, as you can get reinfected after you've recovered, you can also get reinfected with the resistant strain. So moving forward, here are the time series comparing all three. And again, the way this is kind of coded right now, your uninfected is not including your vaccinated. So here you have a vaccinated curve about 50%. So just keep that in mind for now. But you can see that as you have resistance and a vaccine built in, that resistance is really increasing the number of people that get infected. But ultimately, it doesn't change the final fractions very much because the vaccine is not affected by the resistance. It's only the antibiotic treatment that is. So scanning through some parameters, this was kind of interesting to me. This was not a result I was expecting to see. But as we change the rate of resistant strain development, it actually, aside from the 0 term, it actually stays pretty constant. And I have some more exploring to do on this. But what it comes down to is pretty much it advances the time scale of the disease. And we will see that a little bit soon, a little bit with the sliders. But here are people stopping their disease, or stopping their treatment, I'm sorry. But there's basically 2 treatment options, which is SAT, self-administered treatment. And this has a completion rate of about 53%. It's pretty poor. But you can also do this DOPT, which is direct observed preventative therapy. And so in DOPT, you actually have healthcare representatives administering every single dose to the patient. And this saw completion percentages of about 85%. So still not great, but much better than self-administered treatment. And there is a slight difference. I'm going to do a little bit more kind of diving into whether that's significant or not, but that's how it stands now. And so here is changing the rate of resistant strain development. So this is kind of what I was saying earlier. As we increase the rate at which resistance develops, if it'll load. Okay, so as you can see, as we increase the rate that this resistance develops, the ending fractions remain pretty much the same, but the time scale of the disease is just advanced. Until we get to 0, when there's no resistance developing, and you get a model that looks pretty similar to just the simple model with the vaccine included. And then here are my references. The inspiring paper, I didn't really pull a lot. I simplified their model a lot and made a lot of changes to it. But it is the paper that gave me the initial idea. And then these are all just papers that I referenced, whether my R naughts were reasonable. And they reported, 0.26 for the Netherlands and up to 4.3 in China. The prevalence of the resistant strain of TBs, where I got, how often they develop resistance, length of treatments, things like that. So is there any questions or anything that I can go back to and try to examine in more detail for anybody?
I had a couple questions about the main model.
Yeah.
So do individuals in the SP, SN, and NP groups all have different rates for going into the T and R groups? Like, why are they separated?
So they have different, let me go back up to the original model. So they have different infection rates and different death rates slightly. So they have to be separated because, your smear positive is your 100% infectious relatively to the others. And then your smear negative is about 75% less infectious. Your non-pulmonary is not infectious at all. So because of those differences, they do have to be separated. However, they move to recovery and treatment the same rates. So they're all identified. This chi is basically the rate that cases are identified, and then Z is successful treatment of the disease. So.
Okay. And then why don't recovered individuals why do recovered individuals go straight to the L group instead of the S group?
So that's a good question. They don't move back into the susceptible population because they show what's the wording on it? They show persistent but imperfect resistance to reinfection, whereas susceptibles do not have any resistance to infection at all. So I keep them, I keep them separated out just because they have 65% resistance to being reinfected.
Okay, cool.
Yep.
Other questions, comments? That was a lot of material. I guess there are a couple of things I thought about, which I'll type up just in terms of, it might be helpful, for example, to have, you've got your main plot, but you could have a plot next to it where you plotted, for example, the fraction of the level of number infected with the wild type versus the number infected with the resistance. You could see how those balances change. It might also be interesting to plot the deaths versus time from the virus. I could say virus from the bacterium. so that you could get a sense of whether how effective you are at keeping people from dying, which may or may not be quite the same as keeping people from getting infected.
Yeah, I agree. I do have the deaths of.
Right. Right.
I do have a zone where deaths go, in case I wanted to do those comparisons.
I think that could be interesting.
Yeah.
And you mentioned that you're normalizing by the total population to keep everything safe, but it might be good at the very beginning to plot what the total population versus time looks like, so that somebody knows what they're normalizing against.
Okay.
Just so there's a little more background there. I'm a little surprised that your reference simulation, half of your population gets TB. In other words, and I don't know what the numbers are. If you look at Europe before the invention of antibiotics, what fraction of people actually had TB? That's a number you could look up. And
Okay.
maybe it was 50%, because you're seeing that basically in your case, in your model with no treatment, half the people or more get TB. And
Yeah.
I don't know if that is consistent with what happened historically. I mean, I know in Europe in the 19th century, TB was one of the main causes of death, and so it was very significant. But I don't know whether they're documented what fraction of the population had it. In other words, if we had no treatment, would it go back to 50% of the population? Maybe. I just don't know. So it'd be good to do a sanity check on that number.
Okay.
What's the incidence in a population community with no treatment?
Right.
It was pretty bad. It was called the White Plague for a reason.
Yeah.
Which of course is why you have lots of 19th century things like Traviata about dying of tuberculosis.
And Poe, Edgar Allan Poe wrote a lot about it.
Yeah, it was romanticized in a funny way, but it certainly killed lots of people.
Mhm.
And I guess it also was interesting to people because it killed the well-off as well as the poor.
Mhm.
Although the poor were more vulnerable because of poor nutrition, these kinds of things. But I don't know. I'm sure. I bet Wikipedia will tell you what the incidence of tuberculosis in, say, England in 1880 was. But it would be interesting to know that. But I think this is very nice. You've really got. You've explored a lot. I think people could learn a lot from playing with this result. Any other comments, suggestions? Again, please, part of your assignment is to type up some critiques and suggestions for your classmates so that they can improve. And again, I mean, if people need more time to get everything done, if you email me, I can certainly give you an incomplete. And then if you need another week to finish things up, I'm not saying you have to do it. You're welcome to finish. But if people want the extra time to finish up, I can certainly give you an incomplete and give you the grade in a week or two or whenever you're finished. It's up to you. Depending. I mean, if you're about to graduate, if for some reason you're going to graduate at the end of the semester, I can't give you an incomplete. And I'm not encouraging you to do what some students have done in the past, which is take an incomplete and then not do anything on the project for a year, and then face the fact that if the incomplete isn't resolved, you fail the class. So I'm not suggesting that you should do an incomplete, but if people feel that you'd rather have an extra week or two to work on it, finish it up, I can do that. Just email me and let me know what you want. Again, I'm not pushing you one way or the other, but it's your choice. It is an option. I don't push the option because it's better to be done with things, especially next semester. If the semester starts and you have 4 classes that are keeping you busy. The last thing you want is to have to finish a class from the previous semester. Okay. Other comments? That was a great presentation, both of them today. Everybody's been doing a great job doing your presentations. The variety of topics has been great. Do people want to take a break or shall we plow on? You want to take a 5-minute break? Yes?
I'd like that.
Works for me.
Okay. Okay, so let's come back at 6:30 and we'll continue with Devin, right? You're here, Devin, ready? Okay, good. I'll see you I'll see
Yeah,
you.
I'm good, Jack.
I'll see you everybody so we'll queue, why don't you queue up and then we'll start back in 5 minutes. Okay. So, well, Devin, is it okay to record you?
Yeah, that's fine.
Okay, great. Then take it away.
All right. So my project is over Ebola spread and different intervention measures in Liberia. So just a little background about Ebola. Ebola is a rare deadly virus that originated in Africa. There's actually two strains of Ebola. There's the Zaire Ebola virus, which is in Western Africa, and the Sudan Ebola virus, which was the first one to be recognized. And that one's in Central Africa. I think the first case of that was actually recognized was in the 70s. And it was near the Ebola River, so that's the namesake for it. So the initial symptoms of Ebola virus are fever, body aches, diarrhea, and vomiting. And as the disease progresses, there's some more serious symptoms such as organ failure and uncontrollable bleeding. So there's been periodic outbreaks throughout history of Ebola, at least in recent years, and it spreads through bodily fluids. And so this graphic I thought was really good. It talks about the how Ebola virus came to be. So it's originally in animals. A lot of people think, or a lot of scientists think that the first animal to get it was a bat. And so animals can spread it between themselves. And then if a human hunts or eats one of these animals that's infected, that's known as a spillover event where the first human becomes infected with it. And then, so after that, humans can transmit the disease to one another. A few things that they talk about that are common transmission sites are their funeral practices. I don't know exactly the culture over there, but I guess they touch the dead body and can transmit the fluids. And then there's unprotected healthcare workers and just other like healthcare workers that are, or family members that are caring for the ill. And then I think also sexual activity is one of the ways that it can be spread. And then it also mentions some survivors can have tiredness and muscle aches and also stigma in their communities. And so I also brought a few facts about Ebola. So the most recent outbreak that probably a lot of people remember was began in March of 2014. This is over in Western Africa, which is the Zaire Ebola virus. And in total,
Sorry, we're having a little trouble with your mic.
really?
Yeah, a lot of the time it's fine and then you cut out. I'm not sure. Are other people, maybe it's just me, maybe it's on my end. Are other people having trouble hearing Devin continually?
Yeah, yeah, I think we're all having the same problem.
Can you hear me any better now or no?
When you said or no, it was fine, but it was, try talking again.
Okay, my headphones finally connected. Can you hear me now?
That sounds good.
Okay, cool. So like I said, the most recent outbreak was in March of 2014. That's the one that we probably all remember where a few cases got into the US in Texas and New York, I think. And in total, in Africa at least, there was 28,616 total cases and 11,310 total deaths. And in the country that I chose to focus on, which is Liberia, they had 10,000 cases and almost 5,000 deaths. And then the public health advisory on this disease was finally lifted in March 2016. So it was almost 2 years that it was active. And then there are still Ebola cases, just there haven't been any big outbreaks lately. Most recent one was in June of this year in the Congo, which is actually the Sudan Ebola virus. So the paper that I decided to replicate is called Modeling the Effect of Comprehensive Interventions on Ebola Virus Transmission.
It explores different intervention strategies. Let's see, there's something in the chat. Can you guys hear me? Sorry about that.
It's on and off. It sounds like, is that a wireless mic or a wired mic?
Wireless headphones.
I'm not sure what.
Devin, try changing the microphone to the computer one.
I did have it on that originally.
Sometimes AirPods just don't work for me. So
Yeah, I have the same problem as well with AirPods as well. Yeah.
All right, we're back on the computer. Is that any better?
I can hear you now.
Let's hope it stays that way.
Okay.
Okay,
I'm sorry, I don't want to be a pain, but it's a great
No.
talk, so I want to make sure everybody hears it.
Yeah. So this paper explores different intervention strategies using ODEs. Some of the intervention strategies that they look at are early isolation. So when people begin to develop symptoms, they're actually not infectious until they reach a certain date milestone. I can't remember what it is. So they want to recognize that early and get them into isolation. And then there's vaccination. The reason I chose Liberia is because that's the only country that has data for vaccinations. And then safe burial practices. As I mentioned, people who are dead but have not been buried can still transmit the disease. And then media education of the citizens. So when the media like warns people to be safe, I don't know if they probably didn't wear masks, but like personal protective equipment and stuff when they're taking care of somebody with Ebola. And that actually had quite a bit of impact. I think the transmission rates were about half as much as they usually are when people are educated on it. That's not something I really got to dive into because I was struggling with some other things in this paper, but I definitely want to add that as I go along. Okay, so my equations and the key variables. So there are 9 epidemiological states for this model. There's susceptible, which everybody starts out as susceptible. Vaccinated. E1 is latent infected, but they don't show symptoms yet, so they're undetectable. E2 is also latently infected to where they can't transmit the disease, but they are showing symptoms, some of those early symptoms that I mentioned. And then I is infected, which I guess a better term for it would be infectious because they can spread the disease to other people. J is isolated. D is dead, but as I mentioned, they can still transmit the disease until they're buried. And then R is recovered. And so I have the equations that the paper used listed here, but I'll get into that a little more with the arrow diagram in the next slide. Okay, so this is the arrow diagram for my model. So everybody starts out as susceptible. For those who can be vaccinated, they can transition into the vaccinated category at the rate of the vaccination rate here is Z times the amount of susceptible people. And then susceptible people can also become infected if they're not vaccinated. So this rate is, these betas are the human to human transmission rate. So we have the transmission rate times the number of infected people plus the transmission rate times the number of isolated individuals times epsilon here, which is the relative rate that that isolated people can be infected or infectious, I guess. And I was surprised to learn that that's almost half or roughly a half. So even if you're isolated, you still have a 50% chance of transmitting it or transmitting the disease as compared to somebody in the I category. And then we have beta D here, which is the dead person transmission rate to alive people times the number of dead people. And then all of this is multiplied by the number of susceptible people and divided by the total population here, which is N. And for vaccinated people going into E1, it's the same exact equation. except we add here N, which is the vaccine efficacy. So if the vaccine's not 100% effective, then people can transition from the vaccinated category to infected, or early infected, I guess. And so E1, as I mentioned, is undetectable infected. And so they can transition into having symptoms, basically E2 at the rate of K1 times E1. And K1 is just the time that it takes to transition between these classes. People who start showing symptoms and recognize it can go into isolation at the rate of FT times E2. And FT is just the rate that, I wrote it down here wrong. It's the rate that people become isolated when they recognize it. And if they don't go into isolation, they go into the infectious class at the rate of K2E2. Some infectious people do become isolated after they are infectious. So this is alpha times 1, where alpha is the time from the infectious class to the isolated class. Isolated individuals can recover at the rate of 1 minus delta, which delta is the, where did I write that down now? Oh, it's the case fatality rate. So if they don't die from it, then they're in that class, times the time that isolated people are removed, either due to death or recovery, times the number of isolated individuals. And then infectious people can recover or die in the same sort of manner. So they can die at the rate of the case fatality rate times the time that the infectious people are removed times the number of infectious people, or they can recover at the same thing, it's just 1 minus delta. And then, don't think I mentioned this, isolated people die at the same rate. It just uses gamma R, which is the time isolated people are removed. And then it has this D going off because it shows that they're still infected. So this is, or infectious, and this is the time from death to burial times the number of dead people. All right, so I will move over into my solarium demonstration. I just list all my references here and same sort of stuff, parameters. So when I originally started doing my model, just trying to figure out the time series of it, for some reason I was getting numbers way above what they should be. And so I met with Professor Glazier actually, and he suggested that I just try dividing the total population by a certain number. And that actually helped me. So what I figured out is that there's like pockets of infectious diseases or infectious people, like locations. And so not everybody's going to have the risk of getting infected if they live in an area that's not, doesn't have outbreaks. So the first thing I did was trying to find out that normalization rate. So here I have the original model with what they did. And you can see that I'm getting 160,000 cases at the peak here. I guess 160,000 isolated individuals at the peak here. When in the actual model, I'm actually only getting, or in the actual paper, they only have 500. So what I put in the paper as sort of an educational tool is trying to figure out how to match that. So if we slide this normalization factor, it divides the population by this amount. And so if you test that out and continue to move it, the total number of individuals goes down. And I found that just over 400 is about the right amount to get to 500. So that's kind of what I used throughout the paper. I used the normalized data instead of what they did. I'm not sure how they got this without including something like that, or maybe I just missed it in the paper. But that's something that took me quite a while to figure out. And So then after that, I started doing just the basic models. I did at first an unvaccinated model. So I just set the vaccination rate to 0 along with all my equations here. And you can see that we get about 10,000 total cases and 5,000 total deaths, which is good to see because the death rate is roughly 50%. And that matches what I saw on the paper right here. See about 10,000 cases and 5,000 deaths here. Yeah. And then, so after that, I did a vaccinated model with the numbers they provided. They had a vaccine efficacy of about 55%. And in recent years, those vaccinations have improved. So some of them are almost 90% now. But with the data they used, we see there's about 7,000 total cases and about 3,500 total deaths. And so I wanted to explore the vaccination a little bit further. So I added some sliders along with a couple buttons. So this is this is their model right now with the 55% vaccine efficacy and the vaccination rate that they gave. If I decide to remove vaccination, it gives me the numbers that I originally had. And so we can adjust these numbers and see how each of these variables affects the model. You can see that vaccine efficacy, for some reason, doesn't have that great of an effect on the total cases, but the vaccination rate does. If we lower that vaccination rate, we see a lot more cases. And if we increase the vaccination rate, there's a lot less cases. So we can reset those values, and we can also remove vaccination with this button here. And so another thing that I did, this model was actually published in late 2015 before the outbreak was actually over. So I looked at the World Health Organization's actual data for the entire outbreak and wanted to fit my model that didn't include all of the time period for that to the actual data. So I started off just by plotting the total cases in Liberia here. And I also did the total deaths, which fit my model pretty well. And then I did I just ran my model again, and it plots both total cases and total deaths. And then I did a minimizer function to see, first I'll run, originally how my model fit. This model is not very good. You can see that it starts off well and it hits well at the top, but this sort of leveling off period or slowing down period messed up. So I did a minimizer function for that to get it to fit. And this takes a minute, but I can show it in the results. We'll see how it works for a second. So it does get closer, but I'll go back to the presentation to show how it works. So first off, I just have the basic total cases, total deaths model. This is my unvaccinated model, which that's what they provided in the paper. And you can see that my model fit the total cases number pretty well, although mine might have been a little steeper than theirs. And then I also included the vaccinated model here, which has less cases.
Then you completely cut off. Like we barely heard what you said in the previous slide.
Can you hear me now?
Hello?
Yeah, it's frustrating because half the time you're fine, and then half the time it sounds like a real loose connection in one of the mics.
Yeah, I don't know what's going
I'm
on.
just using my computer mic. I don't know.
Because you're fine now. So
Uh,
I guess it may be blanking you. So if you try to talk louder, it might actually help.
Okay. So like I said here, I have my unvaccinated model, which fit pretty well with theirs that they provided in the paper. And then I have my vaccinated model, which shows less total deaths, and they did not include one of these graphs in the paper, so I can't compare it to that. And then here is the end of the fitting. See again at the beginning and the end, it fits pretty well, although the total cases are less, but I think it's this leveling off period, the slowing down period that caused my fitting to not do so well. And then in my continuation of the model, I want to look at the spread in the other countries that they had. The other countries were Guinea and I can't remember the other one right now, but another country right next to there. And implement vaccination data just based on what Liberia had listed and see how it affected that model. And then I also want to look at parameters and values from other viral diseases and compare the models, because even though Ebola is not so prevalent now, there's always viruses popping up, as we've seen. And so this model could fit those kind of diseases well if they share the same sort of characteristics. And then I need to, before I submit it, get more into the media and safe burial effects. I didn't have time for that because I was struggling with sort of the normalization of the data. I couldn't figure that out for the longest time. And so I want to look at how media education and safe burial affects how the disease is going to spread. And that's all I got.
Okay, thank you for making the effort to deal when the mic's not working. It's very frustrating for you, I know.
I'm sorry about that.
Comments, questions? Somehow when you talk loud, it's fine. So there must be a noise cancellation that's kicking. Comments,
Hey,
questions?
I was just gonna say I really like the implementation of the reset button and the other buttons within the project. I think I might take that.
Yeah, you can thank Tyler for that. He showed me how to do those.
Thanks, Tyler.
Yeah, as I say, next year if I do this, I'll make everybody. I'll have the presentations 3 weeks before the end of the semester. People will complain, but that way people have time to do a round of corrections and learn from each other. Because I've learned a lot working with you individually, and I've tried to pass it on to people, but seeing each other's presentations, I hope we learn from it. I thought it was very nice. Ryan, any other comments? I was going to say that this slowdown you're seeing is probably a change in social behavior, where as people get sicker, they probably are self-isolating, would be my guess. And so you could have something where that infection rate or the number of contacts goes down as the rate of infection goes up. And that would give you what a Michaela called a Michaela, but we talked about Michaela's constant. And I suspect that would be what's happening here. That once people know things are bad, they don't travel as much, they don't interact as much. And so that thing which is a constant in your model would stop being a constant. It would depend on the infection rate. Mm-hmm. The only other thing I had was it might be nice to plot not just the aggregate number of cases and deaths, but the number in your I and J categories as a function of time, maybe in a plot next to it, because that's really the derivative of these slopes. But sometimes it's sort of interesting to see how many people are infected, the most people are infected, when does it happen, those kind of things might be nice to plot. You just put the plots side by side, for example. But I thought in general, it's pretty interesting. The fact that there's a vaccine for Ebola is sort of amazing. And the fact that it works at all is sort of amazing. There are very few diseases that are as lethal as Ebola.
Yeah.
So fortunately, the transmissivity is not that high, but it's. But I thought that was very nice. The only other thing is that the vaccine is, you're assuming that the immunity, if you get it or if you get vaccinated, is infinitely long. And that's probably not true, but of course the data sets you're working with would be over a period of a year or two, couple of years. So you probably wouldn't see the drop off of efficacy.
Yeah, I think they did mention in a different paper that there's a very low chance, like quite a ways down the road, that you can get it, but within the period of a single outbreak, probably not.
Well, I guess also the probability of getting it is low enough that the probability that the same individual is exposed twice is not high, unless you happen to be out in the bush near bats or something, or marmots or whatever you're getting exposed by. But if you live in a city, because it's so the infections are so localized, you probably don't have to worry. It's not sort of the opposite of COVID, where here you have a very high lethality, but it stays local, and that's called burnout. Diseases that really kill everybody. It's like the science fiction movie where everybody on the space station dies. Well, once everybody's dead, there's nobody to spread it. Well, of course, there's always in the science fiction movie. There's always some nitwit who comes into the dead space station and manages to catch it. But in general, diseases that have very, very high mortalities don't spread because they kill everybody before they could spread. But it's interesting that some people made it to the United States carrying Ebola. So that's great. Other comments, questions? Again, I really hope people will send their comments so I can aggregate them tomorrow and send them on to people. I think it's good, and it's good to see other diseases like tuberculosis, Ebola, not just COVID, and see how these play out. And I hope Callie, Devin, Brian, and company that working on treatment and Nico working on treatment and the idea of treatment and vaccination. I hope you could, seeing each other's presentations, you can share ideas and use it to sort of refine your presentations. So each one of these diseases has a sort of a different dynamics, a different set of interesting questions. Great. And Devin, I agree with you. I don't understand, looking at that paper, why they didn't mention that their reference population isn't the full population of the country. It doesn't make sense. I think they must have done what we did, or what you did, but I don't know. But they should have said that. One problem, and Mercedes ran into this too, is that just because a public paper is published, even in a good location, even if it's good by good people, doesn't mean that it's right. And it can be wrong in different ways. It can be wrong because it's really wrong, or it can be wrong because there's a typo in an equation, or they left a parameter out, or there's a typo in the parameter. And so it's certainly possible for a published paper that you pick to seem very attractive and not be completely correct. And one of the reasons replicating papers is important is because just because it's published doesn't mean it's right. So I appreciate everyone taking the effort to do this. Other comments? Any final comments for Devin? No. So Brian, you're the last of our list.
Yes. I was gonna say, can I use the restroom first?
Please go ahead.
Okay.
No worries. The issue of vaccination is sort of a tricky one. We had one talk, of course, last week talking where there was a delay equation, and talking about I mean, we saw today a talk about tuberculosis, which is slow disease. With COVID, it's a fast disease and it spreads. Oh, did I tell you I talked to somebody on Sunday who was interesting for two reasons. One, he works at Google Health, which is a good connection to have, because they do fascinating work, potentially good employer for people later on. Although he's more of an AI guy doing patient data mining rather than the kind of modeling we do. But the second thing is he's the first person I've met who had COVID twice. So he got it. He was in London in March. He thinks he got it on the plane coming back. And he was diagnosed definitively with a PCR test. That was positive. He got over it. And then I guess because he had it, he assumed that maybe the company assumed that he could travel. And he got it again in November. And again, the PCR diagnosis. So he definitively had it twice. And there are a few people who've been reported in the news for having had it twice, but he's the first person I know of who's had it twice and had it both the PCR test both times. And so 6 months between the first infection and the second, which is a little bit worrying about the duration of immunity. Now, he may have some specific issues that made it different, but it gives you at least a ballpark idea of what a reasonable duration of immunity might be. 6 months. The other thing you said, which was also sort of worrying, is that the second infection was worse. He was much sicker. It could be that he was exposed to a higher dose of infection. It could be that it was a different strain. Could be that there was a secondary infection that caused it to be worse. Many possibilities. But there was a worry from the beginning that maybe like dengue, second infection could be worse than first. And if that were something that were automatic, you'd expect to see it with the vaccine studies. Because in that case, you might expect that if you got it after you were if you got vaccinated, you were less likely to get it. But if you got sick, you were more sick. And the studies didn't show that. But if it only happens when the vaccine starts to wear off, there hasn't been enough time. And so there's a worrying possibility that at least some people might actually get it worse after being vaccinated. That still doesn't mean it's not a good idea to be vaccinated, but it means that maybe the revaccination frequency would have to be higher so that you never get to this regime where having low immunity is worse than having either high immunity or no immunity. Clearly having low immunity is worse than having high immunity. But the idea that having low immunity might be worse than none is actually sort of a little disturbing. And again, that's seen for dengue, so it's not impossible. Anyway, I thought while we're waiting for Brian to come back, I thought maybe that would be, it's not science because it's an N of 1, but I thought it might be of interest to people to hear about that. I don't know. I know some people in the room have had COVID. Has anybody else in the room had COVID twice? Has anybody in the room had COVID twice? Does anybody know anyone who had it twice?
Not yet.
Not yet. So yeah, still.
Twice.
Sorry?
I know somebody who's had it twice.
What was the interval between first and second infection?
First I heard of him getting it, I think, was around July, and then I heard him getting it like last month.
That's very short. So I wonder what's going on there. That's unusual. I wouldn't say it's impossible. It's just maybe unexpected. That when it's that short an interval, you might think that they never cleared it. More like the tuberculosis case where you have latent tuberculosis that can last for a long time.
So that's about 4 months or so.
Well, maybe it's long enough. I don't know. It's an interesting question. As they say, in a year we'll know. A year seems like a long time, though, to wait to find out. Although they've certainly, I mean, they developed that Ebola vaccine amazingly fast compared to any other vaccine in history. And now, of course, they've developed this vaccine for COVID even faster, piggybacking a lot on what they did for Ebola. Just the way remdesivir is piggybacking on that too. Totally unrelated viruses, but it winds up some of the treatment strategies seem to overlap, which is interesting. Okay, well, Brian, is it okay to record you?
Yeah, it should be fine.
Okay, great. Take it away. Thank you for being, thank you to both Mercedes for being first and to Brian for being last. I appreciate it.
No problem. So let's see. Let me share my screen. Okay. This should hopefully be something that everyone sees. Okay. All right. So my project was on the SARS-CoV-2 vaccination model, and that's sort of the title that I've given it. Another title that kind of fits better, I think, is more like an SVIR model with kind of birth and death rates implemented in. So a little bit of biological background on COVID-19. And this was sort of covered in Callie's presentation, but essentially the first known case was originated on November 17th in 2019 in Wuhan, China. And as of this date, some of the statistics that I pulled off of Worldometer is we currently have about 73 million total cases worldwide, and about 1.6 million deaths, and about 51 million have recovered. So I'd say it's pretty widespread at this point. And in the United States, we have about 17 million total cases and about 300,000 deaths. So it's been steadily ticking up. I believe like last month it was only about 200,000, but it recently sneaked up to about 300,000 in the last month or so. So I think this kind of model would be able to help sort of model this in the future. And some more biological background is that definitely it spreads through either airborne or droplet transmission. Some of the most common symptoms are fever, dry cough, and tiredness. And it has an incubation period of around 2 to 14 days, in which cases are asymptomatic, which means that the person is infected and they don't have any symptoms. So that's kind of important since we talked about Ebola sort of and other diseases being not really spreadable because they kill their host. COVID is kind of interesting because it's kind of able to have an asymptomatic effect on its patients or its victims, so to say. So I based this vaccination model was sort of is sort of a sort of a augmented SIR model from the beginning of the first day of class, essentially. So we have a similar susceptible to infected, and then we have infected to recovered, and then recovered goes back to susceptible because we don't know how long necessarily the immunity will last after you sort of recover from COVID. And then we have down here a V, so that essentially means you go from vaccination, you go from susceptible to being vaccinated, and then at some point you could either go back into infected or you could go back into susceptible. And some of the variables that I use in this project, B is the birth rate, so we have the birth rate going into the susceptible, and then we have D being the death rate. So this is the arrow going out from S is sort of the death rate due to COVID, or not due to COVID, death rate in relation to susceptible people, and so on and so forth down the line. And we have a variable D2 for the death rate due to COVID-19. So that mainly, we put that right in the infected slot, because generally speaking, once you're infected, you only have death rate due to COVID from that area. And finally, we have D prime being the vaccination rate. So that kind of goes in relation to S into the V, which is the amount of people that we have, the population of the total population that we have vaccinated. And then we have alpha 1, which is down here, being 1 minus the vaccine efficacy. So that's sort of the arrow in terms of, it's on the other slide, but that's sort of the arrow in terms of vaccine to infected rate. And we have also beta being the probability of infection per encounter, gamma 1 being the rate of loss of immunity. So that kind of refers to the recovered moving back into susceptible, and as well as the vaccination moving up into susceptible. And finally, we have N being the number of encounters per day, and MU being infection duration. So as you can see, this kind of is it sort of is an augmented SIR model, in that we sort of just tacked a V on here, but hopefully this sort of represents sort of the flow of how this vaccine or this virus works. Some of the mathematics behind it is, excuse me. So we have S to I being the infection rate, I to R being the recovery rate. And the B in the equation is definitely just the birth rate. Death rate of S is the D times S in this equation. D2 times I is the death rate of I, and then which is this is only in terms of death rate due to coronavirus. The death rate of R, which is essentially D times R. Gamma 1 times R, which is the recovery immunity loss rate essentially. And vaccination rate per person, which is this arrow down here. The vaccination immunity loss rate, and then the vaccine to infected rate, and of course the death rate of V, which I'm not sure if it's been put in here. So some of the initial assumptions or conditions that we start out with this model with is that our initial susceptible population, I decided to go with about 300 million, since I'm trying to model the United States population, and the United States population tends to be, it is around 328 million people. And like before, sort of like in the original like SIR model, our initial infected population starts with 1, and we have no recovered starting out with. And that kind of jumps to the Jupyter Notebook. But before we go over to the Jupyter Notebook, I'd like to kind of state the purpose of what this notebook is, since I sort of realized that this is something that needs to be established. The purpose of this notebook is essentially to offer a comprehensive tool to anyone who would need it, in hopes of predicting a variety of future scenarios in relation to the coronavirus. And I think that's essentially the essence of why we do modeling in the first place. In this case, I'm hoping to sort of illustrate different scenarios based on when we start vaccinating and how effective the vaccination rate is, and how this relates to future results in terms of in terms of future scenarios. Okay. Does anyone have any questions so far? Okay, then I guess I'll just keep going. So this is the SVIR birth death COVID-19 model. And sorry, I have something. My throat hasn't been great today. So essentially, currently this model is sort of unfinished, and I'd like to finalize it and add some of the things, and that's something that I put in the slides. So we'll go over that later. But up here is essentially our model that I illustrated before in the slides, and we have a couple of things such as being able to test the vaccination efficacy rate, as well as sort of births and deaths. So this first exercise that I tried to piece together in this model is that I wanted to show everyone a kind of the graphical interpretation of some of the variables within the project. And this is sort of very slapdash together, but essentially the D1 in this case represents the sort of like the natural death rate. And then the D2 sort of represents the death rate due to COVID. We also have time versus total population. So you can see how the total population moves down as sort of deaths go on. And then we have, these are all the variables, S, V, I, and R. Sort of, these are basically just graphical representations of them versus time. And then we have disease deaths, and then time versus R naught down here. And essentially what I wanted to illustrate with this exercise is that in my antimony or in my code, I put in a start time and an at start time function. So these two lines, or these three lines right here. And essentially what I wanted to illustrate to the person who's looking at this application is that by looking at the start time, you can see like different sort of points in the graph where it fluctuates. And I wanted to tell them, or sort of illustrate the fact that by changing the start time of when you start vaccinating for this pandemic, or so to say, you can see different graphical representations of how it kind of plays out. So I'm going to try to put that into show right now. So here we have D prime being the vaccination rate in the beginning. And essentially our start time is 365. So 365 is kind of the representation of the amount of days before we start vaccinating. So this is a scenario in which case there's a pandemic. It starts from one infected person, and then after about 1 year, a vaccine comes out, and our vaccination rate goes from 0 to about 5 times a year. So if we just let that run out, you can see that now the graphs kind of sort of have this account for 365, which is around this point. And this graph kind of like moves. I think it's a little bit better represented in this graph, where you see the different populations kind of get abruptly cut off as the vaccination rate kind of comes in. So this is sort of the first exercise I wanted to illustrate, which is that you can effectively change certain timescales based on when you get vaccinated. So the second exercise that I put in, and mostly to the help of the professor and some of my peers, is that I wanted to illustrate an exercise in which we try to see the what happens when you change the efficacy and the start time or the immunity duration. So these three sliders down here represent a little bit of different values. This efficacy up here represents vaccine efficacy. The start time, which I don't think I've been able to get to work currently, but give me 1 second. Okay. So this efficacy rate is definitely just the vaccine efficacy rate. This start time is basically the amount of days before you start vaccinating. And this immunity is essentially how long you have in terms of immunity. So if we decided to say that the efficacy rate was about say 0, oh, hold on. That's odd. Thankfully, I have an old model that we could try out.
I think you just turned off the vaccine, didn't you, when you commented out that line in the code?
Probably, maybe. Oh, right. Let me just put 365 here. Okay. And that should, in theory, okay, there it is. So essentially, since our vaccination rate is about 5 times a year, by moving the efficacy rate up slowly, you can see sort of a difference between the original graph and sort of the amounts of people who are saved. And basically the difference here in sort of the graphical representation is that the red line represents the original graph, so our original situation without sort of change, and then the blue line sort of represents our changed graph. So, and the difference between these graphs at any given point represents the amount of deaths that sort of have been saved. So if we move our slider from around 0.10 to about 0.5 or so, you can start to see that the difference is sort of in the millions, essentially. So this is about 2 million, roughly, people that have been saved just by having a higher efficacy rate in terms of vaccination. And I think mainly this part in particular is cumulative or curative, in that 0.9 is significantly, or 0.95 is significantly better than 0.9. But as you can see, even just the difference between like a Pfizer vaccine being 0.9 and the Moderna vaccine being 0.95 has a huge difference in terms of about 1 million or 500,000 people being saved just based off of the efficacy rate. And that's sort of what I wanted to illustrate with this exercise, which is essentially what kind of difference do you see, and how many, and what is the difference, and what does that difference represent, and how many people have been saved?
Brian, I have a quick question.
Yes.
How does this difference depend on the actual vaccination rate? Right, because this is just efficacy, right?
Yes, this is efficacy.
So what happens if you, let's say, increase the, what happens for the different, do you know what happens for the difference, here if you increase the rate?
Yes, I believe so. It would essentially be configuring this D prime over here, or give me 1 second. Efficacy. Yes. So essentially, I think I could do this, but essentially, if you wanted to configure the actual vaccination rate, you could most likely just input a different slider into the graph, and that would sort of help illustrate the graphical differences. I could give it a shot if you'd like me to try.
I was just curious. It would be interesting to see how sensitive that this difference is to the vaccination rate. Let's say you have like that difference is very important if your vaccination rate is very low, but if your vaccination rate is very high, that 5% difference in efficacy might or might not be as important. And I don't know, like from the model, I think it's something interesting.
Right. Okay. All right.
Yeah, I don't think it would be too hard to add a slider for the rate of vaccination. So that D prime, I mean, you may make it 0, but then say you've got D prime equal to 5/365. You could make it 1/5/365 or 10/365 and see what the effect is there. The other thing you might want to think about, it's minor, but you have that nice reference curve, which is the unvaccinated curve. But it might be nice if you actually have a version where you could have 2 sets with sliders on the same plot. So the background one, you could say, is compare what it is, compare the death curve for a 90% vaccine with a 0%, 95% vaccine. In other words, be able to have one slider for the efficacy of the red curve and one for the efficacy of the other.
Okay.
And a small thing, I have been trying not to interrupt, but just a general thing, and this is something to do when you're polishing things. Everybody should remember to label the axes, both the X and Y axes of all their graphs. And some you've got them mostly labeled, but not all of them. So that's because that's the last thing you do. The other thing to do would be to have a key. So there's a label function where you could say the red line means this and the blue line means that. So add a key to so people know which curve is which. Again, some of the plot functions just plot, m.plot does that automatically. Plot array, you have to put those things in by hand. Again, these are tiny points when you're cleaning up, but I wanted to say that because it's something everybody needs to remember to do to make sure their axes are labeled and you have something that says which curve is which color is which.
Gotcha. Okay. I'll implement that next. And I just wanted to say that this definitely I think vaccination rate would be something interesting to implement, and probably not something very hard to implement, because currently the E prime in this code sort of represents the lagging. It represents the sort of how many vaccinations you get in a single year. So that's why it's a 5/365, because this is assuming that we have people getting vaccinated 5 times a year, and being able to slide that up and down would sort of give us an input on how sensitive this graph is to that kind of change. The other thing I wanted to highlight specifically is the immunity. So currently we have the immunity set to 1 year, but let's say we wanted to implement maybe Tyler's friend's example, where you had about 4 months or so in between. 4 months is about 120. So if we move this down a little bit to about 120, you can see quite quickly that that the death rate soon rises above its original, and that's mainly because the immunity of a virus is pretty significant when sort of implementing or trying to implement models. So in Tyler's friend's case, this is sort of what it would look like. And finally, sort of the last exercise I wanted to illustrate is this graph is a graphical representation of the difference between the 2 graphs put up here. And it's just something little small, but generally speaking, if you increase the amount of immunity, you sort of prevent deaths from happening. And that's sort of the model in its full entirety.
Okay. Okay, great. I thank you for, I thought that it was very helpful to have you do the introduction for what your aims were. That was good. And I liked the way you used the sliders for some of that. Other comments, questions? I hope a lot of people have done vaccine models. Each one of you has explored slightly different aspects of vaccination. And as I say, it's great for people to talk to each other and sort of combine your, I'm sorry, you still have a slide. Let me finish your slide.
No, I think you were good. I just wanted to say that the model it could be used as a predictive measure, and some of the further expansions that I saw from today's slides is that I definitely want to implement some widgets. I don't have to go on and press shift enter every single time, and an expansion on some of the key exercises. I want to polish those, finalize the project, and write some better descriptions and exercises. And definitely implement the labels and a D prime slider, because I think that would be pertinent. And finally, the expansion is that maybe in the future, I could implement some kind of older or younger population SIR, so that this model could be more specialized, and it would be a sort of a specialized tool that people could use to model the future. And that's the entire presentation.
Okay, well, thank you, everyone. Comments, general discussions. I realized this course was a little bit of an experiment because it was all new material. And so I appreciate all of your patience with me while we were exploring this. And feedback about how to teach it better would be much appreciated. I do take those things seriously. And I will probably not tonight, but tomorrow I'll type up my comments on the people who presented today. I already got feedback for the people who presented last week. You've got my comments. Again, please, everybody, do send your comments on your classmates' presentations and suggestions. It's very important that we get that through. And feel free to talk to each other. I mean, the people who did vaccination models, you're all welcome to talk to each other. This is not a place where you have to do everything on your own. Learning from each other is good. And so if I don't know, Kali had something in her model that Brian wants to borrow or look at, I mean, she doesn't have to share, of course, but if she feels like it, please feel free to talk to each other and share ideas. As I say, if you want me to give you a grade on Monday, I need things by Saturday morning at the latest. If you want to take a little more time and take an incomplete, just ask for it. And I can do that. I'm not pushing you to. Everybody did a lot of nice work. But as I mentioned, if you put these things up on NanoHub, they're sort of permanent. And that's a good thing and a bad thing. And the good thing, I mean, frankly, if you put something up and it's not wonderful on NanoHub, nobody will pay attention. So it's nothing, there's no really bad downside to it. But if you put something up on NanoHub and it's good, people notice it and they use it. And so, unlike your typical term paper, which disappears, these notebooks, if you put them up and they're good, get noticed, and so it's an opportunity. And so it's maybe again, you don't have to push a little harder to take advantage of that. But I want to emphasize that you get a DOI, you can cite it as a publication in your CV. And so if it's something you're proud of, it's something you could say, hey, Google or Apple or whatever, I did this work. You can see my work online. And NanoHub logs how many people have used it. So you can say, gee, there are 50 people who actually have used my software and tried it out, which is pretty neat. Which is why I said doing something like a miniature YouTube video, which can also be uploaded to NanoHub. You can do a little self-promotion if you like. Again, it's not required, but it's an opportunity. Over the years, some people have done that. So I'm happy to meet with people more to talk about these projects if you want to refine things. I know, Josh, you're going to be on a plane tomorrow, right?
I will, but I'll be available on Thursday.
Yeah. Okay.
If anyone needs to talk. I'll try to figure out myself how to upload the apps. I'm gonna try to have like a semi-final version of mine, and I'm pretty sure that once you upload the apps, you can always like upload new versions of it. But I have to figure out how to do that.
Yeah, Andy Samoji can help us too on this. Yeah. So those are possibilities. And again, I'm teaching modeling again next semester. It'll be spatial modeling, so the models are a little more elaborate. People don't have to have had this class to take the one next semester, but it's more fun if you have. I don't know, Josh, if you can demo it. Did we ever demo the COVID model, the spatial COVID model to this class?
No, we did not, but I don't know like if we have time. Well,
can you just pull it up? Just why don't you just pull it up on NanoHub and show it?
Just 1 second.
Again, it doesn't have to be COVID next semester. It could be cancer. It could be many things. But we do, all the models we've done have assumed essentially that everything is described by scalars, by numbers. But in fact, as we heard in the Ebola case, the spatial organization of the disease is very important. It matters whether you're next to somebody who's infected or not. And so spatial structure in models is something that's very important. And also in the body. And so
I'm gonna start sharing my screen here now.
Okay.
So this is an example of the type of model that we will be covering next semester. In this particular case, we are simulating, it's basically the type of it's basically a special version of the type of within host model that we covered in class, the ODEs, right? It's a little bit more complicated in terms of how things are represented, but conceptually it has the same. It has cells that are uninfected, which are in blue here. Cells that are early infected, which are in green. And then cells that are late infected, releasing virus, you will see them later on. And then, so now that cells is releasing virus and we can actually see it. So these are the immune cells also, because this is a 3D model. So on top of this layer, there's another layer where cells, immune cells are crawling, trying to, and then they kill the immune cells that the infected cells they come into contact with. And then we have also the virus.
You have to hit run again.
Yeah.
It's really slow tonight. Usually it runs a lot faster than that.
Yeah, and I don't know. Yeah, the whole plot, like displaying the plots and stuff, that sort of like makes a lot of it slower. But it's basically almost not running on my end.
Well, let's get, there it goes. It's starting. Let's give it a second.
Yeah. So
But it normally runs a lot faster than that. I'm sort of puzzled.
yeah, and if I had a local version, I would show it, but I do not. You can also run the software locally. See there, you can see now the virus being released, starting to be released here. Then you can see the immune cells, and then the immune cells, they the same way we saw models that have interferon, we have also a cytokine that also diffuses in the across the tissue and recruits further immune cells. So it's very similar to the within host model that we walk you guys through in class. So this is a newly infected cell. And if you, yeah, so now the infection is gonna start spreading out outwardly from this initially infected cell. But yeah, and this simulation is running super slow on my end. And there, I mean, this is just one type of application that this spatial modeling can be used for, but we might also cover cancer and other type of stuff that James circulated a tentative outline of the class. So here, for example, yeah, this cell died because it came into contact. It was infected, and then a effector immune cell came into contact with it, and that cell just died because it had produced enough virus that then the cell undergoes apoptosis because of virally induced cell death. I'm gonna stop it there because it's running super slow, but the basic idea is here.
So if you're interested in that kind of modeling, and you can do all sorts of things with it, that's what we'll do next semester. And so you'd all be welcome to join if you feel like it. Anything else? Last comments as a group before we break? I know it's been a long slog and people are probably tired and hungry. I can smell food in the background here, so I'm hungry too. Any comments, suggestions? I just want to thank everybody for being part of this and working so hard. I really appreciate everything you did. I appreciate the ingenuity and ideas you had in your projects. And I've really enjoyed working with you. And so I want to thank you again. If people want to meet one-on-one the next few days, I'm always available. Again, we'll do our best to help you make sure these things get uploaded in a nice form so that you can have them on NanoHub and people can play with them. If there's nothing else to say, I just want to thank you again, and I'll be in touch with you in the next day or two with comments and working with people who will need help. Okay? Thank you. Good night.
Thank you, Dr. Glazier.
Thank you.
Thank you.
Okay.
Thank you, Professor.
Thank you. Good night, everyone. Bye.